So we're gonna dive deeper into our trig functions, keep working with them, but specifically we're gonna look at some special angles and then talk about more connections that we have with all of our different trig functions. So the first special group of angles we're gonna talk about are 45, 45, 90 degree triangles. What that means is your three angles are 45, 45, and 90 degrees. So we're gonna look at this triangle in quadrant 1 and see what happens with it. But because the two angles are exactly the same, this does end up forming an isosceles triangle. So the two legs are exactly the same length. In reality, I could assign a number to them like 1 and 1, but I'm gonna use a more generalized x because I need to for the second equation. But if those are our two legs, then our hypotenuse again is going to be r. So we do have a nice connection, however. I'm going to be able to rewrite r in terms of x. So if I use my Pythagorean theorem, one side squared plus the other side squared is going to be my hypotenuse squared. Well, x squared plus x squared is 2x squared is my hypotenuse squared. So if I go ahead and take a square root, that gives me the square root of 2x squared. Now in theory, I can take the square root of each of these, and this gives me the square root of 2, and then the square root of x squared. And really what ends up happening when you take the square root of x squared, you get the absolute value of x. But I'm concerned with just quadrant 1 right now because we haven't really talked too deep as to what happens for other quadrants. So really our x value is going to be positive. So this hypotenuse I can instead write as the square root of 2 times x. So if I want to find what cosine of 45 degrees is, I really could use either of these. It's the adjacent over the hypotenuse. Same thing, I go right here, it's the adjacent over the hypotenuse, which is just x over the value of r. So we have x. The value of r in this case we can write as something special. It's root 2 over x. So you notice our x's end up canceling out and we get 1 over root 2. Which again, we don't like that radical in the denominator. So if we rationalize that, we times it by root 2 over 2. Cosine of 45 degrees is root 2 over 2. Sine of 45 degrees ends up being exactly the same because the opposite and the adjacent are the same length. So the side opposite is x, and the adjacent, or the hypotenuse, is root 2 over x. But it is our y value over r, just happens to be the same as x in this case. So you really end up with 1 over root 2, which is exactly the same thing, root 2 over 2. And then tangent of 45 degrees is going to be opposite over adjacent. So opposite over adjacent results in 1. So this is really nice when I have these three trig functions. 45 is one we're going to be able to evaluate exactly. For other angles like 10 degrees, not going to be able to do the same thing. It's just because this is a very special triangle with special properties. And likewise, if we have a 30, 60, 90 triangle, so one angle is a right angle, the other two have to be complementary. So if one is 30 and one is 60, then we can go ahead and still find a nice connection between these ratios. So this one's a little bit more complicated for how I can find this connection. So what I'm going to actually do is I'm going to duplicate this triangle to make a bigger one. So we have our right triangle here, and I'm going to just duplicate it so that we have the same triangle on the other side as best as I can at least. Okay. So this triangle has 60 degrees here, 30 degrees here, my right angle at the bottom. This is x, this is y, and then this is our hypotenuse. If I flip it over, all it does is it makes this still a 30-degree angle, this still 90, this still 60. this side would be x, and this side would be r. But if you notice, this is 60 degrees, this is 60 degrees. These add up to 60 degrees. So we actually end up with an equilateral triangle. So all of our angles are 60 degrees, which means that every side length is going to be the same. Okay. So here's our value of y, and really this side length in total is x plus x, which is 2x. So this full side is going to be 2x. But really what that also does is, because it's equilateral, these have to be 2x as well, okay? And now I can go ahead and I can figure out what y has to be in terms of x, because this is a single x here, a single x here. And now that I know my hypotenuse in terms of x, I can go ahead and use the Pythagorean theorem. So x squared plus y squared has to equal my hypotenuse squared. Well, 2x squared is going to be 4x squared, which then if we move this x squared to the other side, that gives us y squared is 3x squared. And then same thing, I go ahead and take a square root. So our y value is going to be root 3, and then the x squared and square root cancel each other out, but you technically get absolute value. Again, I'm focusing just in quadrant 1 right now, so it just pops out as an x. Okay. So really, my triangle, every side can be written in terms of x, just like the last one. So here is my 30, 60, 90 triangle. 90 degrees here, 60 degrees here, 30 degrees here. We have side x. This is root 3x, and this ends up being 2x. So now I can figure out sine, cosine, tangent of all of these, starting out with cosine of 60 degrees. Here's my 60-degree angle. It's adjacent over hypotenuse. So that gives me x over 2x. Again, the x's end up canceling, and cosine of 60 degrees is a half. If I look at cosine of 30 degrees, 30 degrees is right here. That's going to be adjacent over hypotenuse. So that is root 3x over 2x. And again, the x's cancel. So cosine of 30 degrees is root 3 over 2. If I move on to sine of 60 degrees, 60 degrees is here, so I want opposite over hypotenuse. That gives me root 3x over 2x. So those end up canceling, and sine of 60 degrees is going to be root 3 over 2. So something to notice, sine of 60 is exactly the same thing as cosine of 30. And that's important for us because 30 and 60 are complementary, which is where this co comes from. So when I go to find sine of 30 degrees, it's really going to be the same thing as cosine of 60. So sine of 30, sine is opposite over hypotenuse. So that's x over 2x, giving us 1/2. Then finally, moving on to tangent of 60 degrees. Tangent is TOA, so opposite over adjacent. That gives us root 3x over x. So that just simplifies to root 3 over 1, so root 3. And then looking at tangent of 30 degrees, opposite over adjacent gives us just a flip of this. So you end up with 1 over root 3, okay? Which is exactly the same when you rationalize, as you got to times it by root 3 over 3. So this gives us root 3 over 3. Okay. So again, I'm going to make some notes because it also ended up happening up here. 45 and 45 are complementary, and sine and cosine are exactly the same thing here. So this is going to lead into our idea, but just as a note, I want to add that. Cosine of 30 degrees is exactly the same thing as sine of 60. And then likewise, cosine of 60 degrees is the same as sine of 30. So there's a really nice connection between complementary angles. So these are trig values that you are going to have to know like the back of your hand if you're moving on to calculus. You want to be very fluent at being able to know what cosine of 60 degrees is. And then when we get to other important angles, we're about to do reference angles, we're going to have to be able to figure out pretty quickly what cosine of 150 degrees is, what sine of 150 degrees is. So we're going to build something that's called our unit circle once we get through a radian measure. But you do want to know all of the first quadrant angles. If you can identify those, it's going to be very helpful for your class overall. So if you think about your first quadrant, 0 degrees is our first quadrantal angle, and then we end at 90 degrees. Halfway in between them is 45 degrees, which is a special angle. And then we also have 30 degrees and 60 degrees as two key angles. If we know sine, cosine, and tangent, then we know the reciprocal functions. So I'm going to specifically write it as sine, cosine, and tangent because tangent is exactly sine over cosine. Okay. So if you can build this chart, you then in turn will be able to build the unit circle, and you'll be able to have all of these values because there are going to be times when you're not allowed to use a calculator on exams because you need to know these thoroughly. So if I want to figure out what sine of 0 degrees is, I'm going to look here. Sine of 30 will be the value here. Sine of 45, sine of 60, sine of 90. So I can go ahead and I can copy in all of those different angles that we just went through, but I'm going to show you a technique to also figure that out. It's very important though that you set up the table this way every single time to utilize this. So sine is going to start out with 0, and then you're going to increment it by 1 until you get to 4. To find sine of 0 degrees, you're going to take the square root of this number and divide it by 2. So this is square root of 0 over 2, which is 0. Sine of 30 degrees is going to be square root of 1 over 2, which is 1/2. Okay? That's exactly what we figured out back here. Sine of 30 degrees is always going to be 1/2. Sine of 45 is root 2 over 2, which you can't simplify. Sine of 60 degrees is root 3 over 2, and then sine of 90 is root 4 over 2. Root 4 is 2, so sine of 90 is 1. Okay. To then figure out what cosine is, you do the opposite. You start by 4 and then increment it down to 0. So ultimately, you take this row and you just flip it around. So cosine of 0 is going to be 1. So this one comes here. Then this comes here, just the same as taking root 3 over 2. Cosine of 45 is root 2 over 2. Cosine of 60 degrees is 1/2. And then this ends up being 0. Okay. Now to figure out tangent, you just take sine and divide it by cosine. So sine of 0, or tangent of 0 is 0 over 1. Which is just 0. For this next one, it's a little messy, but basically what ends up happening is you just keep those numerators, because in here, you would have to take 1/2 and you need to divide it by root 3 over 2, which is the same thing as taking 1/2 and multiplying by 2 over root 3. So you end up with 1 over root 3. So again, it doesn't matter what that denominator is. The r doesn't matter. You just take the y and the x. So here you end up with 1 over root 3, which you do need to rationalize. That's root 3 over 3. When I go for tangent of 45 degrees, I'm taking root 2 over 2 and dividing it by root 2 over 2. So this is just 1. Then when I go for tangent of 60 degrees, the same idea, just those numerators end up mattering. It's root 3 over 1, which is root 3. Then when it comes time for tangent of 90, this would be 1 divided by 0, so this is undefined, okay? So you do really, again, want to know these. You are not going to be able to use a calculator for a lot of your tests, so you have to be conscientious of making sure you understand these angles and their trig values. It will become second nature at some point, at least in the sense of you can kind of do it in your head by thinking about what quadrant you're in, but you really need to know the trig functions evaluated at these special angles, okay? So now we're gonna go into where these names actually come from, not actually sine, tangent, all of that, but these co-words we keep seeing. So this is our concept of co-functions. So if you think about some of these special angles, sine of 60 degrees is root 3 over 2, but that's exactly the same thing as cosine of 30 degrees. So sine and cosine. So this is equal to cosine of 30 degrees. Tangent of 60 is going to be root 3 over 1. Well, that's the same thing as cotangent of 30 degrees because you take the adjacent over the opposite. And then likewise, if I take secant of 60, this is really the flip of cosine of 60 degrees. So cosine of 60 degrees would be 1 over 2, so it is 2 over 1. That's exactly the same thing as if I take cosecant, which is 2 over 1. That's the hypotenuse over the opposite. So sine and cosine are called cofunctions. Tangent, cotangent, secant, cosecant. Cosine, cotangent, cosecant are all called cofunctions. And that co just comes from that word being complementary because the two angles in here are complementary to each other. So if you look at alpha plus beta in our triangle, because one angle is a right angle, these two have to add up to 90. So alpha and beta are complementary. So if I look at sine of beta, so is opposite over hypotenuse. So this is side A over side C. Well, if I look at that perspective from alpha, A is the adjacent, C is the hypotenuse. So that is cosine of alpha. So if I know one angle, I automatically know cosine of that angle as well. So in general, we have 6 different cofunction identities. If you take sine of an angle, it's the same thing as cosine of its complementary angle, which you find by doing 90 minus theta. So 30 degrees would make the complementary angle 60. 15 degrees would make the complementary angle 65, or 75, so it adds up to 90. And then you can look at it this the other way. If you have cosine of an angle, it's the same thing as sine of its complementary angle. Then tangent of an angle is equivalent to cotangent of the complement. And if you started with cotangent, it's the same thing as tangent of the complement. And then finally, we've got secant of theta. Its cofunction is cosecant, and the angle in here is the complement. So if you start with cosecant, secant is the cofunction of the complement. Okay? So let's try a few examples of this, and then really we're going to spend a ton of time with reference angles. Okay? So we're going to rewrite in terms of its cofunction. So starting with cosine, this is going to relate then to the sine function. And on the inside, I put the complement of 49.8 degrees. So subtracting 49.8 from 90, cosine of 49.8 is the same thing as sine of 40.2 degrees. If I'm starting with cosecant of 13, cosecant and secant relate to each other. And then again, I've got to find the complement of 13. So I do 90 minus 13 degrees. So 90 minus 13 would give me 77. So cosecant of 13 degrees is the same thing as secant of 77. Okay? All right. So the last thing we're really going to talk about are reference angles and how we can utilize these key ones to then help us figure out sine, cosine, tangent in different quadrants. So again, you can always draw that triangle like we did before, but realistically, reference angles are exactly what we're doing. So a reference angle is an acute angle formed by the terminal side and the x-axis. So in quadrant 1, if that's where your terminal side lies, so maybe it lies right here, your reference angle is an acute angle, so it's formed with the x-axis. This would be our reference angle. Let's call it alpha. If our angle ends in quadrant 2, your actual angle might be here. It could also be flipped all the way around. But your reference angle you're going to use is whatever this angle is right here. So it's formed with the x-axis. If you land in quadrant 3, the angle I'm really going to be concerned about is this one right here. So that's going to be how we create our right triangle to figure out sine, cosine, tangent of whatever angle this is where the terminal side lies. And finally, if you are in quadrant 4, maybe it looks something like this. Your reference angle is this one right here, okay? So to show you with some actual numbers and kind of explain what you're going to do to find cosine, sine, tangent of your angles, you're always going to find the reference angle. So if theta is 150 degrees, then its reference angle is the following. So I'm going to draw my xy plane. This is 0 degrees, 90 degrees, 180 degrees. Okay. I don't like using formulas for reference angles. I like drawing a picture and seeing what's going on. So 150 degrees is somewhere in between here. So the terminal side of my angle lands here. So this is theta, which is 150 degrees. My reference angle is then this angle right here, okay? So if I look, this is 150 degrees. To get to 180, I need to go 30 more, or essentially, from 180 degrees, I need to remove the reference angle. So alpha is found by taking 180 and subtracting 150 to give us a nice acute angle of 30 degrees. Okay, so this value here is 30 degrees. So what I would do is I would have that 30-60 triangle right here, but since I'm in quadrant 2, I know my x value would be negative. So I'm going to figure out what cosine of 30 degrees is, what sine of 30 degrees is, what tangent of 30 degrees is. And that will tell me the trig values of sine of 150, cosine of 150, tangent of 150. Because I'm in quadrant 2, that immediately tells me the signs, positive or negative, of the different trig functions there. So to try to summarize that, we use cosine of 30 degrees and sine of 30 degrees to find the values of cosine of 150 and sine of 150. Okay. The quadrant the angle is in tells us the sign. So whether it's positive or negative. Okay. So to give you an example of this, we can use our little chart again if we're not super familiarized with this. But cosine of 30 degrees is going to be root 3 over 2. And sine of 30 degrees is a half. Okay. So again, I can go back up to my chart that I built here. Look at 30 degrees. Sine of 30 degrees is a half. Cosine of 30 degrees is root 3 over 2. So that tells me when I look at cosine of 150 degrees, it's the same number. And same thing, sine of 150 degrees is the same number. But because I'm in quadrant 2 for this angle, remember all students take calculus, sine is positive here, but cosine is negative. So immediately that tells me I have to put a minus here, and this one's good. It is positive 1/2. Because you end up using the same 30, 60, 90 triangle to find the different sides of each of these, okay? So these reference angles are stuff we've already been using, but again, it just helps us for these special angles. Well, let's get some practice just trying to find reference angles. We're gonna do a few examples. They're not gonna be pretty ones. They're not gonna be necessarily ones that are special. Maybe they will, we'll see. But the first one, 223, definitely not going to correspond to a special angle because those all end in 0s or 5s. So I'm always going to start by drawing my XY axes. So this is 0 degrees, 90 degrees, 180, and 270. So this is good. If I look at 223, it's somewhere in between here. So I draw the terminal side of my triangle. And then again, my full angle would be starting at 0 and going here to 223. My reference angle is just an acute angle. So this is alpha. So if I want to find alpha, this total angle is 223, but I don't care about any of this stuff up here. So from 223, I'm going to remove that straight angle of 180. So angle alpha is found by taking 223 degrees and subtracting 180 to give us the acute angle 43 degrees. Okay, so that is our reference angle. Looking at B, I have 750 degrees, which is way more than 360. So you can start here at 0, but really it makes more sense to start at 360. Adding 90 degrees would give you 450. 90 degrees again is 540. 90 degrees is 630. 90 more degrees lands you at another spin, that's 720. And I'm still not at my angle 750. So adding another 90 degrees gives me 810. And now I'm doing better. 750 is less than 810. So my reference angle ends somewhere in here. So I'm going to go ahead, or my terminal side ends somewhere in here. Just going to draw it. Could be to scale, might not be. But my actual angle alpha is I started here, once around to 360, once around to 720, and then up to here. So that is my 750 degree angle. What I need though is just the small acute angle here, alpha, okay? So if I subtract 360, that doesn't give me an acute angle. Really, what I have to do is from 750, I need to remove that amount before it, which is 720. So my angle alpha is found by taking 750 and subtracting 720. So that gives me 30 degrees. So it is one of our special angles. Not drawn to scale, but that's okay, all right? Let's try one more of these, negative 135 degrees. Again, draw a nice little picture. Here is 0 degrees. Now I need to go backwards. So this is negative 90, negative 180. And now I'm good. My terminal side of my angle is lying somewhere in here. So I started here and I went backwards. This is negative 135 degrees. So what I need is this particular angle alpha, okay? You can use negatives if you want, but this full distance is 180. You want to get rid of 135. You're basically finding the supplementary angle. This is x, this is 135. They have to add to 180. So angle alpha is going to be 180 degrees minus 135 degrees, giving us a reference angle of 45. So again, if I wanted to find sine of negative 135 degrees, it will deal with sine of 45 degrees. And since I'm in quadrant 3, sine is negative there. So this would be negative root 2 over 2, okay? So let's try an example of this where we're gonna find all of the 6 trig functions for one of these angles. And the angle we're given is negative 240. So again, I wanna draw a picture just while I'm getting used to all of this stuff because it's gonna help us out a lot. This would be 0 degrees. I'm working with negative, so let's go negative 90, negative 180, negative 270 up here. So negative 240 is somewhere in between here. Okay. So I would start here and then go around. That is negative 240. My reference angle alpha is right here, okay? Again, you can use negatives if you want, but you don't have to worry. This is 240, just the opposite direction. I need to get rid of this piece down here to get alpha. So from 240, I'm going to subtract a straight angle. So it's 240 minus 180 to give us a reference angle of 60 degrees. So this angle here with the x-axis is 60. So we're going to use sine of 60 and cosine of 60 to find all of the other trig functions. So we use that sine of 60 degrees is going to be root 3 over 2. And cosine of 60 degrees is half to find all of the other trig functions. Okay. Since theta, our actual angle, is in quadrant 2, we can use our saying, all students take calculus, only sine and hence cosecant of theta are positive. Okay. So if I look at sine of 240 negative degrees, it is positive, and it's exactly the same thing as sine of 60 degrees. You get root 3 over 2. And then cosine of negative 240 degrees is going to deal with cosine of 60. But again, because we are in quadrant 2, cosine is negative there. So it is negative 1/2. If I look at tangent of negative 240 degrees, you could write this in terms of tangent of 60, but realistically, once you have these two, you have everything else. So you don't need to go through and memorize that either. This is equal to sine of negative 240 degrees over cosine of negative 240. That gives me root 3 over 2 over negative 1/2. Well, you got fractions and fractions. You can go ahead and multiply by the reciprocals, but really times top and bottom by 2. Those end up canceling. That gives you root 3 over negative 1, which is negative root 3. To find cosecant of negative 240 degrees, I just flip sine. So that becomes 2 over root 3. Again, we don't like that, so we go ahead and rationalize by multiplying by root 3 over 3. So that gives me 2 root 3 over 3. Okay. Then to find secant of negative 240, it's the flip of cosine. So cosine of negative 240 is going to be negative 1/2. So you just flip that and it gives you negative 2. And then finally, cotangent of negative 240 degrees is we just flip tangent. So that gives us really negative 1 over root 3. And again, we don't like that, so we rationalize by multiplying by root 3 over root 3. So that gives us negative root 3 over 3. So those are your 6 different trig functions for this one particular angle. Okay. So again, super important to know those quadrantal angles. And the more you do this, the more you'll get comfortable with what sine of 30 is, what cosine of 30 is. You won't. So I just have one last example that we're going to try. We're going to find all possible values such that cosine of theta is 1/2 and theta is between 0 and 360 degrees. Because realistically, there's actually a lot of angles where cosine of theta will be 1/2. It all just depends on how many revolutions you go around the unit circle. But if you think about this, our cosine function has to be positive. So cosine of theta is going to be positive in quadrant 1 and quadrant 2, or not 2, 4, because that's down at the bottom. So quadrant 1, 2, 3, and 4. But using our all students take calculus, cosine is positive in 1 and 4. So if you think about where cosine of theta equals 1/2, this implies that our reference angle is going to be 60 degrees. Okay. So I'm going to be working with some multiple of 60 degrees essentially. So my first angle is right here with this terminal side. My second angle would be down here. So angle 1 would be I start here and go up, and that forms a reference angle of 60 degrees. My other one has this being the reference angle, 60 degrees. Okay. So if cosine of theta is equal to 1/2, this tells us one possible angle is the one in quadrant 1, which is 60 degrees, or it's this angle starting here and going forward to give you a 60-degree reference angle. So this is 0 degrees and also 360. So the other possibility we have is we subtract 60 degrees to give us 300. So there are two possible answers for this. Cosine of theta equals 1/2 when theta is 60 degrees, or when theta is 300. Because those two different angles that give us positive 1/2. And then really from here, you can find a ton more angles that also have an output for cosine of positive 1/2. You can go around the unit circle again and again and again. You can go the opposite direction and subtract 360 degrees. But all of those will land on the same terminal side and give you that same exact reference angle. Okay? Which is why these reference angles are so important for us, because it tells us a lot of information.